Okay, so today I have a pretty interesting integral, and this is the integral from 0 to pi of the arcsin of sin x by root 5 by 4 minus cos x. And what's interesting about this integral, and the first thing that you might notice, is that the inside part of the function, so sin x by root 5 by 4 minus cos x, has the exact same zeros as the bounds of the integral. So what that means is, when I have sin x by root 5 by 4 minus cos x equal to 0, and sin x is equal to 0, x is equal to 0, and x is equal to pi, because these are the zeros of sin x. What that actually means is that when I have the inside of this function, the x-intercepts are 0 and pi, and this gives us a little insight as to what we can do with this information. Since arcsin is increasing, we can just take the derivative and find the maximum or minimum to see when the function increases and when the function decreases. And if we do that, we can split up the integral, and it'll really help in our u subs in case it's really complicated. So what we can do is we can just write this as the integral. And by the way, all you have to do is take the derivative of this function. Taking the derivative of this function is really trivial, but it's really wrong. And since it's a formula, you can try it yourself. But the maximum point between these two values is pi by 3, or I guess x is equal to pi by 3 and 1. So the function increases from 0 to pi by 3, and it decreases from pi by 3 to pi. So we can rewrite this integral as the integral from 0 to pi by 3 of arcsin sin x by root 5 by 4 minus cos x. So this is the increasing part of the integral, and then we have the decreasing part of the integral, which is from pi by 3 to pi of, again, arcsin of sin x by root 5 by 4 minus cos x. So just to conclude what we've done, we found out that the zeros of the inside are exactly the zeros, or exactly the bounds of the integral. So what this allows us to do, since arcsin is increasing, it makes it a lot easier to find out when the function itself is increasing and decreasing. And it increases from 0 to pi by 3, and it decreases from pi by 3 to pi. And based on this information, we can really easily split up the integral. So this is our new split up integral. And what we can do with this is we can make a u sub. The most complicated thing about this is the fact that there's this entire inner thing, arcsin of sin x by root 5 by 4 minus cos x. And to simplify that, we can just do the most obvious u sub, and that is u equal to sin x by root 5 by 4 minus cos x. And what this means is that we can actually solve for one of the variables sin x or cos x, and we can actually solve for cos x in terms of u and then make the substitution more easily, because it will be a lot easier to do that, because sin square x, once we move this to the other side, is 1 minus cos square x. So what I'm saying is, if you move the denominator to the other side, u root 5 by 4 minus cos x is equal to sin x. If we square both sides, so squared, squared, and squared, we get u square 5 by 4 minus cos x is equal to sin square x. And what this means is, since sin square x is actually equal to 1 minus cos square x, this is the identity sin square x plus cos square x is equal to 1. We can really isolate u, and we can find cos x in terms of u, and it'll make the entire substitution a lot easier. So all we have to do is we have to make 5 by 4 u square minus u square cos x, and then we can just move this to the other side, minus 1 plus cos square x equal to 0. Grouping together like terms, we get cos square x plus minus u square cos x plus 5 by 4 5 by 4 u square minus 1 equal to 0. And again, this is a pretty standard quadratic equation. So what this means is that we have cos x is equal to minus b. So that's u square plus or minus the root of b square. So since b is minus u square, it will be u to the power 4 minus 4ac. Since a is 1, we get 5 by 4 u square minus 1 by 2 since a is 1. And at first this might seem a little confusing since we have two values, but this actually makes perfect sense as we've already split this integral up into the decreasing and the increasing parts. So having these two values, it really helps us. Uh, it helps us visualize and more importantly, just be able to make the substitution because the positive value can be used for the increasing part and the negative value can be used for the decreasing part, and that makes sense because obviously the solution of cos x is going to be smaller or negative for when the function is decreasing and is going to be positive and it's increasing. So all we have to do is we have to once again differentiate and then we'll be able to take du by dx, and well, you know the drill for u subs, but I'm just going to skip that because once again it's a really trivial process. It's just doing the same thing we already did. It's just differentiation. So I'm just going to substitute u here inside the integral. So once again, just remember that cos x is equal to u square plus minus root of u4 minus 4 times 5 by 4 u square minus 1, and this is really just minus 5 u square plus 4. So all we have to do is substitute this into the integral with the multiplying factor, which you can find by differentiating. I'm not going to differentiate it here since I did this on paper, but you can try it yourself. It's going to be the integral from 0 to pi by 3. So now we're just applying the u sub and making it in terms of u. And actually, what's interesting about this is the bounds are now changed also because we have this u sub. The bounds are not 0 and pi by 3. Remember, when you make a u sub, one of the most important things which you have to do is you actually have to plug the bounds into this new value for u. And if you do that, you'll find that the new bounds is 0 to 1 if you use u. And now instead of this arcsin of this whole complicated thing, we get arcsin u. So this is arcsin u. And then once again, I'm not going to differentiate it again, but for the increasing part, it should be the positive. So it should be arcsin u 5 minus 2u square minus 2 root u to the power 4 minus 5u square plus 4, and this whole thing should be rooted as well, divided by u to the power 4 minus 5u square plus 4 du. And it's also made this a lot easier to solve because 1 and 0 are a lot simpler than pi by 3 and pi. So now that we have this becomes plus the integral from 0 to 1 of the positive parts, that's arcsin u, and our multiplying factor for the positive part of the solution is going to be the same thing but 5 minus 2u square plus 2 root u to the 4 minus 5u square plus 4 by, again, u square minus 5, sorry, u to the power 4, that's my bad, u to the power 4 minus 5u square plus 4. So now that we have, I'm sorry for my handwriting, this really long expression, so we can just add the integral since the bounds are the same, and arcsin u is common, so we get this is the integral from 0 to 1 of arcsin u. And then adding these two is really easy. I mean, they have the same denominator, so it's just root 5 minus 2u square minus 2 root u to the power 4 minus 5u square plus 4 plus this entire thing. So it's just these two added, and then this is the denominator. So instead of writing this entire thing out, this is just going to be arcsin u I'm just going to call the sum of these two since they're so long to write and they're pretty similar to each other. F of u by the root of u to the power 4 minus 5u squared plus 4. Actually, since we already have f, maybe we should make it g. So this is g. I'm sorry for the confusion. Let's change it. du by root u to the power 4 minus 5u squared plus 4 du. And once again, g of u is just this entire thing. It's going to be 5. Actually, I'm sorry, man. Yeah. It's going to be root 5 minus 2u squared minus 2 root u to the power 4 minus 5u squared plus 4 plus root 5 minus 2u squared plus 2 root u to the power 4 minus 5u squared plus 2. So just the sum of these two things. I'm just calling it g of u because it's so long and important, right? So this is actually pretty simplifiable, if you can believe it. All you have to do is you have to square g of u. So g of u is going to be the sum of these two. So what's interesting is that if we square g of u, it's easy to simplify. So g of u squared is equal to 10 minus 4u squared plus 2 root 5 minus 2u squared minus 2 root u to the power 4 minus 5u squared plus 4. And all I've done here is I've taken the sum of these two and I've squared it to get rid of the first radical. So after you square it, you get, so 2ab, right, because you're squaring it. Again, the other part of the radical with the plus instead of the minus, plus 2 root u to the power 4 minus 5u squared plus 4. And so what this means is that this is our solution. So g of u squared is this. And I'm not going to simplify it once again because all you have to do is you have to, so all you have to do here is we have g of u squared is this long entire thing. But what's interesting about this is there are actually two really distinct radicals. And if you simplify this, I'm not going to do it again because it's so long and boring because it's just two radicals in basic algebra. This becomes 16 minus u squared. So it's a really simple expression. And so therefore this entire thing is 4 minus u squared. And this makes it a lot easier to simplify. And since we're dividing this entire g of u thing by the root of u to the power 4 minus 5u squared plus 4, all we have to do is we have to take this 4 minus u squared thing. But first of all, we can just rewrite it again. So this entire thing, sorry for the messiness, but I think you can understand the point. From 0 to 1 of arcsin u, and if g of u squared is this just means that we have the root of g of u squared, so just g and u, of root 4 minus u squared and root u to the power 4 minus 5u squared plus 4 du, and this is going to be 1 0 of arcsin u, and this is going to be, the thing is these two just cancel out, so this becomes 2, since you take the 4 out of the radical and it becomes the root of 4 minus u squared, and then you can factor the 4 minus u squared out of this. So what you end up getting is root 1 minus u squared. You can try it for yourself. So this is our new expression. So now that we have this, our entire integral becomes 2 times the integral from 0 to 1 of arcsin u by root 1 minus u squared. And this is massively convenient since the integral of 1 minus u of root 1 minus u squared is actually arcsin u. So literally all this is, since we have a 2 here, is going to be arcsin square u. And this makes sense because if you think about it, root 1 minus u square, if you root 1 minus u square's integral is actually arcsin u, and since there's a 2 here, all you have to do is square it. You can actually also multiply 2 with it, but arcsin square u sounds nicer, and I think it's cleaner. This is the first thing that came to my mind. So if you differentiate arcsin square u from 1 to 0, this is going to be arcsin square 1 minus arcsin square 0. So this becomes arcsin 1 minus arcsin 0 square, and arcsin 0 is 0 because sine 0 is 0, and arcsin 1 is pi by 2 because sine pi by 2 is 1. So this becomes pi by 2 whole square, which is equal to pi squared over 4, and that's our final answer.